Mindsetters, happy Tuesday to all you grade 11s. You're hanging out with Looney and TK. How are you, TK?
I'm good. And how are you?
I'm good, thanks. What are we doing for the Mindsetters today?
Well, today we will be looking at the force of friction. So there's a lot that I'll be explaining around what is this force. I'll also be talking about components of forces because we can't talk friction without looking at components of forces. We are going to outline this whole section for you nicely. So by the end of it, everyone should be understanding what it is all about.
All right.
Yeah.
Mindsetters, as you heard, TK, we are here to help you. We're going to outline everything nicely for you, and you will understand by the end of this lesson. Remember to hit us up on Twitter and Facebook at Learn Extra. And don't forget to download all your show notes, your videos, and check out all our schedules for this term on learn.mindset.co.za. Just a quick reminder to all you grade 11s, it's the month of love. So we want you guys to show your love and tell us who you love and share all those nice pictures of that special someone or that special thing you have. If it's your dog, if it's your bicycle, if it's your cat, right underneath the post, you need to post your picture. Right underneath the post, tell us why that person is so special to you, or why that thing is so special to you, what they mean to you, and all of that. And remember, you have to be in the picture as well. So you might want to take a selfie with your dog there and just some nice stuff. So remember, show your love. Remember to hashtag it, show your love, and post all your pictures on Facebook. You might just see yourself on TV one day, so make sure you do that, guys. And right now, we are going to go straight to the lesson with TK.
Thank you, Luni. And now, like I said, we're talking friction today. So we're talking force of friction, and there shall be quite a few things that we need to look at. One, we need to talk about the normal force, because when we talk friction, normal force comes in. We will see how the two actually come together. We are also going to show the relationship between friction and the normal force, and therefore explain the types of frictional forces as well at the end. Of course, we don't have one simple or straightforward type of frictional force. We will explain that to you very clearly. Now, let's have a look at the challenge question for today. It's a simple, straightforward question. I hope you will find it easier to work on. It says here, a 10-kilogram box rests on a slope. All right, so there is an angle there, slope that makes an angle of 40 degrees with the horizontal. 1, calculate the maximum static friction. Now we've got one type of friction already stated there, static friction. If the coefficient of friction or of static friction for that situation is 0.25. And B, if the coefficient of dynamic friction, now you see we have got coefficient of static friction and then coefficient of dynamic friction there. If that is 0.15, what is the magnitude of the dynamic friction or that force? All right, so that is what the challenge is about. I hope you will get that easy to work on. Now let's come to that. I've got a whole section here where I'm talking about the normal force. And this whole section is in your notes there, so go there, download the notes, read them on your own, because I don't have much time to deal with all this now, but I want to explain it clearly from situations, okay? We're talking normal force. Say I've got a box, some block, sitting on a horizontal plane like that. One thing we need to remind ourselves about forces is that any object in the universe is attracted towards the center of the earth by a force called the gravitational force. And we do call it weight, if you like. All right, so let me see if we can end up having some arrows here. So if I have gravitational force, okay, if I have a drawing like that or a box like that, I can show the forces acting on it, okay? And part of the forces, or the force that I know will always be there, will be the force of gravity. So that's the first one that I can show you, all right? Quickly undo that. So that will be acting from the center of the object, and we know it is always acting downwards. Now, for this one here, if we have the weight acting downwards like that, and we don't see the block piercing through the table or that surface going down, it means there must be some force acting in the opposite direction to that force, and the two forces must be balanced. So let's try and see if we can get that force there. My force of gravity here, it's not so vertically downwards, but don't mind about it for now. Let me just try and get you the other force. Now, the other force will be this force here, which I call the normal force, okay? And the normal force, of course, will be a force that is, let me see if I can bring it down a little bit. Oh, I can't. Let's see. I can't do that. Fine, it's fine. But then what you need to know is that this force here acts from the surface of the plane where the object is. So this plane here is pushing upwards as much as the block is pushing downwards with the gravitational force. So that is your gravitational force, and that force that balances out the gravitational force is called the normal force, and we use capital letter M to represent it. Okay, now quickly, if we have the mass of this object, say the mass is 10 kilograms, I can find the weight, or what we call the gravitational force, which will be equal to M times G, and that will be 10 times 9.8, and you will get that to be 98 newtons. So I will get that. And if I've got this situation here, it will mean that my normal force as well, the normal force in this situation, normal force will also be equal to 90, or not 9.8, but 98 newtons as well, because it will be equal in magnitude to the weight of the object, but acting in opposite direction. Okay, good. Now, moving down to the next situation here that I have, all right? What I have here is a situation where this box is no more on a horizontal plane, but it is now at an angle. The plane at which it is lying is at an angle with the horizontal. Now, what happens? Let's quickly see what will happen here. Right now, obviously we know, again, there shall be that force, which is the force of gravity. It is always acting in the downward direction like that, okay? Hope I got it at 90 degrees to the surface now. All right, and remember, the normal force is a perpendicular force that acts from the surface onto the object. So definitely it is not in the same direction as, it's the same plane as the force of gravity. This time there is something that is different about them. Okay, let's see what it will look like. So the normal force, again, it acts perpendicular from the surface, so it will be in that direction there. All right, so we can actually come back here and try to see if we can put direction to this. I couldn't get the arrows of that. So there is your FG, and there is your normal force. Now, these forces, when you draw your force diagrams, remember, especially when you're looking at free body diagram, you put a dot and they are all together there because they're acting on one object. Now, look at this situation. For us to be able to get to know the magnitude of the normal force, we will then have to do something with this force of gravity. What do we do? What we do here is to get what we call the components of forces. So let me write here, the component or components of forces. And in this case, we will be looking at the components of our gravitational force. Right. Now, if you look at this diagram here, if I were to find the components of the weight or the gravitational force, I'll have a force going that way. I'll also have another force going this way. And where they meet, okay, where the two meet, I must have a 90-degree angle, and therefore I've got components of forces there. All right? So that's what I have in that way. Good. Now, coming back to this, if you look at this 90-degree triangle here, you would see that you've got an angle there, and that angle is the angle of inclination that is here. So we can say that is your theta. Now, if I've got a 90-degree triangle here, or a right-angled triangle as we know it, I can make use of trig ratios to find the components. Because what I know for sure, if I know the mass of the box, I know what this one is, which is Fg. I know what Fg is. So, and because Fg happens to be the hypotenuse of this triangle, I can work out what this one is. So let me call this one the component of Fg perpendicular to the surface. And this one here, and of course, they are forces, so I have got arrows on them. So this one here will be my Fg parallel. The two will be able, I will be able to find their magnitudes making use of trig ratios. How do I do that? If you look at Fg perpendicular, this is a component that is adjacent to the angle there, and what the relationship that I want to bring about is the relationship that talks to the side adjacent to the angle and the hypotenuse, which is this one. Okay, so adjacent hypotenuse, that should be cos. So Fg perpendicular should be given by this Fg, which we know will be given by mg, mass times gravitational acceleration. That will be Fg times the cosine of the angle, because it is the cos that gives the relationship between the adjacent side and the hypotenuse of a right-angled triangle. So I have already now established how I am going to find the vertical component there. Now, Fg parallel, how am I going to do that? Now let's write Fg parallel here. Fg parallel will be given by, again, the Fg times what? Look at where Fg parallel is. Fg parallel is opposite the angle, opposite that angle. Now, opposite the angle with the hypotenuse, what do I get? I get the sine. Sine is equal to opposite over hypotenuse. So that would mean that my hypotenuse times the sine of the angle should give me my Fg parallel in that way there. So these two learners are called components of force, or of a force. And what is our force here? These two will be components of what our weight is. If we break our weight into two forces, that will be the two components of the weight as we work it out. And from here, then I will be able to know that, look, the weight, I mean, the normal force, let's come back to the normal force here. The normal force is this force that is acting in opposite direction to any force going in that direction. Now, the force going in this direction now, it's this one, is Fg perpendicular. It's not this one. So this time, your normal force is not equal to the gravitational force. It's actually equal to the perpendicular component of your gravitational force. So it becomes very necessary for you to be able to work out this component so that you will say that my normal force here will be equal to the Fg component there of the weight or the gravitational force. I believe you got that story right. And that is why I came straight down here to try and explain this to you as, having enough time. Because if I went through explaining the normal force, it was going to waste our time. But then, when we come back, we are going to have a look at some examples or exercises that we will work on to help us understand more about this normal force and components of forces so that we can be able to solve problems related to that. Thanks, Luni.
All right. Quick shout-outs before you take a break. Sanele Mukove, Apiwe, Daniel Gift, Bafana Tlengiwe, Madoda, and Musa. Thank you so much, guys, for tuning in. Remember, Mindset is the challenge question is on our Facebook page, facebook.com/learnextra. Go try it out. Answer right underneath the post, and we will be back soon. See you after the break. Welcome back, Mindsetters, from that break. Quick shout out to Mukove, Kolofelo Boengi, Renee, Jackson, and Dumsani for trying out the challenge question. More of you must try it out, guys. It is on our Facebook page. Make sure you go check it out. Facebook.com/learnextra. It's right at the top. Some of you are asking, Luni, where's the challenge question? It's right at the top of our Facebook page. So check that out. Answer it, and TK will help you with it right at the end of the show. But now TK is helping you with other stuff, so we'll take it straight back to TK.
Thank you, Luni. Let's proceed with today's lesson, and now we're going to try and apply what we have learned to real situations, solving some of the problems that involve friction and, of course, other forces. We can't talk friction in isolation of the other forces. So let's look at this question here. Question 1, and remember, this is all in your notes, so you can actually work it out during your time as well, even after this lesson, so to see whether you understood what was happening or not. Question 1 says, a 200 Newton force is applied on a 5 kilogram crate at an angle of 40 degrees to the horizontal, as shown. Okay, so you would see this diagram here. As the crate moves to the right, okay, so it moves to the right, it experiences a frictional force of 18 newtons. Okay, then comes the questions. There is the diagram. All right, 1.1. Draw a labeled free body diagram showing all the forces acting on the crate. Now, as the crate is moving there, because we are told it is moving to the right and it's on a surface, on a horizontal surface, what are the forces acting on it? A free body diagram, remember, you don't have to waste time trying to draw what that box looks like. You just have to use a dot to represent that box. So there is my dot. Okay. Now I can fail to show every other force, but at least I can be able to show the gravitational force. This is to those of you that are really battling with these things. So the gravitational force, or what we call the weight, is a force that is acting downwards. Then apart from that, I know there must be a force balancing it out. It is a force called the normal force. So I'll have that. And check. I'm trying by all means to make sure that the magnitude of the two forces, my drawing should show that they are equal, but only acting in opposite directions. Okay? And then there is a force that is acting in that direction here. This is our applied force. And this is the 200 Newton force. That will be enough for labeling. And I can actually show that this is at an angle of 40 degrees, I think. Yeah, 40 degrees. That is the angle there. So that's the force. Apart from that, there is a what? A force of friction. Okay, so there is the frictional force. So I'll have my diagram in that fashion. And remember, this is the dot representing the object there. Now, you have all your forces there. You have shown all of them. Make sure you have arrows to show that these are vector quantities. Then 1.2 says, calculate the horizontal component of the force. Now, if you come back to this force here, all right, this force here, the 200 Newton force, has got components. It has got a horizontal component, and then it also has a vertical component. Okay? So this is the vertical component, and this is the horizontal component. Now, if I move, say I move the vertical component to the right so that I arrange my horizontal and vertical components tail to head, I will have this one here coming like that so that I have a closed figure there. There is my right angle. So I've got a right angled triangle. Where is my angle? 40 degrees there. So I can work out FH, which is what I'm asked to do here. What will be FH? All right? The horizontal component will be given by, this component is adjacent to the angle, so it will be adjacent over hypotenuse, that is cos. So FH will be equal to 200 the cosine of 40 degrees. Okay? 200 times the cos of 40 degrees. And what is that? You can quickly make use of your calculators. There is mine. So I've got 200 here. Oh, what's going on with my calculator here? All right. So I've got my 200. Oh, it doesn't want to help me here. So 200 times the cos of 40. Let me find out here what should actually happen. Okay. Okay, let me try to find out what I should do here. There is the calculator. Okay. Okay, there. Let's see. Oh, my calculator is not helping. All right, that's fine. So what you would have, that will be the component, 200 times cos 40, all right? And that will be your horizontal component. They didn't ask me about the vertical component, but let me just show it to you solo. So the vertical component, obviously, if you have a look at the right angle triangle, you'll see that your vertical component is that one, that is FV. So FV will therefore be equal to 200 times. Look at where FV is on your right angled triangle. It is opposite the angle. So opposite and hypotenuse, that relationship is given by the sine of the angle. So that will be the sine of 40. This one I can quickly work it out without perhaps a calculator, but let's just leave it there. You would be able to find those components. I think with your calculators where you have been able actually to get those answers. Now 1.3, let's have a look at it. It says, what is the magnitude and direction? Yeah, let me find out if I can be able to use the calculator here. Okay, all right. Somebody is helping me from the control room. Let's find the values here back on our horizontal component. What is that value? Let's get it. 153.2 newtons. And the vertical component, it's going to be, all right. Okay, that's fine. I've written down the 153.2 newtons for the horizontal component. So coming to the vertical component, let's find out. This will be now 200 times sine 40. What will that be? All right, that's fine. Let's move on then to 1.3. Now, what is the magnitude and direction of the resultant force acting on the crate? Now, the resultant force acting on the crate, remember, the crate is moving to the right. Okay, this crate is moving to the right. There is the force of friction. There is the force of friction. And in this direction again, okay, with a force of friction like that, okay, we also, not in the same direction, but in the same plane, what do we have? We have the horizontal component, which worked out to 153.2 newtons. Okay, so the two should actually give us the resultant. How do we work that out? The resultant then would be equal to the horizontal component minus friction. What is the horizontal component? 153.2 minus, we are told that the friction is 18 newtons, I believe. Okay, so when it is moving, it experiences a frictional force of 18 newtons. And what does this work out to? I hope the guys stay on. That works 135,21 newtons. Now, this is a force, so it must have direction. Now, it is to the right, the crate is moving to the right. So that is your resultant there. Now, moving on, find the coefficient of friction. Right. All right. Okay, now we have an answer to the vertical component of this force now. Let's just give it to you as well. What? 128,56 newtons. So that's what we have for the vertical component there. Now moving on, coming to 1.4, it says here, find the coefficient of kinetic friction. Now this thing is moving. The coefficient there has to be coefficient of kinetic friction, because there is a difference between kinetic friction and static friction for the same object. Okay, now static friction will always be greater than the kinetic friction. Now look, we have the formula that says if we are to calculate for friction, this time we're calculating for kinetic friction, we will use the mu here, which is called the coefficient of friction, times the normal force. That is the formula that we need to use. And then now the question is, where is our normal force? Do we know what the normal force is? Now, if you go back to the situation, you will see that this object here is lying on a horizontal plane, and therefore the weight or the gravitational force is actually giving you the magnitude of your normal force. So you'll be able to say that this will be equal to this kinetic friction. So what will that force be? The force that that causes that motion, which is your resultant force, okay, will be your kinetic force. That will be 135.21 equals to mu times the normal force will be mass times gravitational acceleration. Now, what is the mass of the block? You are given it to be, the mass of the block is 5 kilograms, all right? So you're going to put it down as times 5 times 9.8, because Fg, remember, because Fg is given by mass times gravitational acceleration. So that's what we've done here, right? Okay, I'm being reminded here. Let me just go back. What is our frictional force? Okay, the frictional force is 18, and that is where I think I went wrong here. I should have, because this is the resultant force, so let's quickly work this one out correctly. This one here comes out to be 18. It is what is given to us. That is the dynamic friction. Okay, so dynamic friction is 18 newtons. That should be equal to that, mu times 5 times 9.8. And what is the answers here? Let's just work it out quickly. So mu would be equal to 18 divided by 49. And the answer is 0.37. Now remember, when you work out the coefficient of friction, you've got newtons divided by newtons. Both these are forces. So actually, your coefficient of friction do not have units. So that's what you have. You don't have to put in any unit there. Now quickly, let's come to question 2. Turbo pulls a 10 kilogram block on a rough incline at 30 degrees to the horizontal using a force of 280 newtons. The force of friction between the block and the surface is 48 newtons. So we don't have to forget the force of friction there. It's 48 newtons. Draw a labeled free body diagram showing all the forces acting there. Okay, now you've got an incline. Okay, so let me use a dot there. From there, you have the gravitational force. So there is your Fg. Now this block here, it's pulled, okay, at an angle of 30 degrees by turbo using 280 newtons. So you will have your 280 newtons, that force there. Now there's also friction of 48 newtons. Friction will always oppose motion, so it will be in that direction there. So that's your frictional force. You can actually say it's equal to 48 newtons. You can do that as well. Now there is the normal force. The normal force is perpendicular to the plane, so I would draw it like that. So there is your normal force. So you have those forces there. Next, calculate the resultant force acting on the block. Now, you need to be careful here in calculating your resultant force. You've got a friction, you've got a component of Fg. Let me just quickly show it to you. Now, there is the F perpendicular, the component of friction in the perpendicular direction. And there is your F parallel. Oh, let me put the G, F parallel. So that is also Fg perpendicular. All right. Now, you need to work out what Fg parallel is, because that will have an impact on your answer when you work out the resultant. How do you do that? We are told that the angle here is 30 degrees. So the angle is 30 degrees. How do we work out Fg parallel? Fg parallel, remember, Fg parallel would be equal to Fg sine angle. And what is that? Fg is mg, and the mass of the block is 10, all right, times 9.8 times the sine of what? The angle is 30 degrees. Okay, so we have got an angle of 30 degrees. So sine 30 degrees. That's what we have. So you would work it out to be 98 times half, and that should actually work out to 49. That should be 49 newtons. Okay? Now it is, this component is also acting in that direction. So they are in the same direction as the what? As the frictional force. Now the resultant force here should then be equal to the applied force, which is 280 newtons, all right, minus the frictional force and minus the Fg parallel. So that will give you 280 minus frictional force is given to us as 48, I believe. There we go. Where is it? 48. Okay, so 48 minus Fg parallel, we've just worked it out to be 49. And let's work out the answer to this one quickly. What does it work out to be? Anybody helping me there? The calculator, I think it's still not working. Let's just have a look at it. 280, it doesn't work out. Okay, all right. So you will be able to get the resultant from there, all right? So let's just move on. Get the resultant there, what the resultant is going to be, and use it. Unfortunately, we have to use it in our second. Are you getting it now? So it's 183 newtons. Okay, so that is the force. Moving on, all right? Coming to the 2.2.2 here, which is the last one on this, we have normal force exerted on the block by the surface. Now, normal force will be equal to Fg perpendicular, remember? Therefore, that will be mg times the cos of the angle. Then you substitute all those things there. Remember, we worked out the Fg to be, Fg works out to be 98. So that will be 98 times 30. times cos 30, sorry, times the cos of 30. Cos of 30 is 0,866, okay? Okay, 0,766. All right, so that should be 0,866. And then calculating that, what does it work out to be? That's fine. Okay, so when you find the cosine of 30 degrees, you'll find it to be 0.866. Now, multiplying 98 by 0.866, you'll get the answer of the normal force here. What is more important here is just for you to understand that the gravitational force in this case, the gravitational component perpendicular to the surface is equal to your normal force. That's what matters there.
All right.
Okay.
Mindset is let's take a break. Before we do, you know, I like to do my shout-outs. Shout out to Sbu Danjabulo Kolofelo Pride, Sharon Siabonga Bongi, Jackson Tandy, Balentle Sizwe Douglas Bonga, Lerato Toby Libia Shalanati Tlapo Siabonga, Ngau Jabulile, Martinique, Klibochile, and Mukove. Thank you so much, grade 11s, for tuning in. We'll see you straight after this break. More learning mindsets, and welcome back from your break. Ngoku TK is going to help us with a challenge question here to TK.
Aha. Ewe ntombi. Ndizobanceda ngoku. Yeah, the challenge question. Let's have a look at the challenge question here. It says we have a 10-kilogram box resting on a slope that makes a 40-degree angle with a horizontal. Okay, so that's what we have. Calculate the maximum static friction if the coefficient of static friction is 0.25. Now, we need to go back to the equation for calculating static friction. Remember that static friction equals to the coefficient of friction times the normal. Okay? Now, the issue here is for us to find out what is that normal. But once we are given the mass of the object, we can easily find that. Think you know that. Now, quickly, you would be able to say this will be equal to, what is our coefficient of friction? 0.25 times. What is the normal? The normal will be the mass times the gravitational acceleration, which is 9.8. Now, what is the mass? 10. So this will be 10 times g. All right? That's what we have. That will be equal to. This will be 98 times 0.25. Let's just find out. Our calculator might help this time. So we've got 0.25 times 10 times 9.8 times 9.8. So what do we have? We've got 24.5. Okay? So that is 24.5 newtons. That's your static friction. All right. The next one, B. It says if the coefficient of dynamic friction, now this time it is moving, it's now 0.15. What is the magnitude of the dynamic friction? Now, the dynamic friction, which is Fk, would be equal to mu dynamic again times the normal. Okay, so that will be equal to this time 0.15 times. What is the normal? The normal again is 98, 10 times 9.8. Okay, so that works out to be, right, calculator, you come handy this time. We have 0.15 times 98, not 9.8, 98. How could I have that? So times 9.8. What do we have? We've got 14.7. Okay, so this is 14.7 newtons. All right, so if you were to draw a graph quickly of showing how this friction from static friction, this is friction, to dynamic friction, all right? You started there, and then this thing was moving. At some point, it came down to that point. Then it continues to move. That is, say, against time. So you would see that when you move from static friction to kinetic friction, it's a huge, huge change. You started from 20-something there to 14 down here. All right, so that's what it is about. Right, I think that is how you were supposed to answer your challenge question. I hope this concept of friction has actually become easier for you to understand at this point. Now that we have spoken about how to find it, how it works, how to calculate for it, and how to get it, making use of components of forces and everything else. I believe you do have questions to ask me. I am going to go back to Luni now and find out what other questions are there that you have posed for me to answer.
All right. From Winnie, she's asking, why did you subtract the Fg when obtaining the resultant force on question 2.2?
On question 2.2,
yes.
Let's go back to it. It was in Fg, but it was Fg parallel. All right. So now let's have a look at it. What's the name again?
From Winnie.
Winnie? Let's just quickly have a look at it. Let me just stand from this side. Winnie, we have got this. Situation here. The force is that one that is applied. And this object here, which is represented by the dot in the middle, it's actually moving up the slope. So the force that is acting against motion is the frictional force, is that force there. But unfortunately, because it is on a slope, we also have a component of its weight. This is its weight. All right. So down here, this whole part here is the weight of the object, Fg. But when we work out the Fg parallel, the component of this weight parallel to the surface, we find that there is Fg parallel which worked out, and it's moving in that direction as well. Sorry about that, making everything look messy here. So there is Fg parallel, Winnie. And then Fg parallel and friction are acting in the same direction. So if I want to find the resultant, it will be that force in that direction minus the force of friction minus the force of gravity parallel, the component. And that's what we did down here, all right, so that we can find the resultant. There is the applied force minus the force of friction minus Fg parallel, which is 49. So there is your force of friction subtracted. Then the force Fg parallel is also acting in the direction of friction. We took it out as well so that we can find what is the resultant. Now, that's why we subtracted the Fg parallel there.
All right. And then from Salvi, how can I find friction in an inclined plane?
Friction in an inclined plane, that's exactly what we've been doing. We can come back to this. If you were to they can actually make you calculate for friction instead of giving it to you. You can be able to do so because it would mean they would have given you other things. Perhaps they would have given you the resultant of the force that is acting there so that you can actually find the frictional force. This is an inclined plane. This plane is inclined because it is at an angle to the horizontal, and therefore you can find the frictional force there. Now, how do we find it? Remember, on an incline, the frictional force would be given by the coefficient of friction times the perpendicular component of that weight, the weight of the of the object you're looking at. So if you're talking incline, remember that this is how it works out. You're not going to use Fg, but you're going to use Fg perpendicular to calculate for frictional force when you are given the coefficient of friction, mu there. Okay?
All right, from Mukove, I'm confused. When do we use sine and when do we apply cos?
Okay, Mukove. Let's come back to this. I'm going to use a simple diagram for you to understand this. Say I had this. There is the weight, or Fg, of a certain situation. Then when I find the components, I find that the Fg perpendicular is that. And the Fg parallel is that. This is the Fg parallel to the plane, perpendicular to the plane, or perpendicular to the surface, parallel to the surface, whichever way you understand it better. Now, you would understand that there you have got a 90-degree angle. Now, the angle of the plane is always there. Say that angle is theta. Now, let's just look at the triangle. If I want to find the sine of the angle theta, it is always the opposite over the hypotenuse. So that will be equal to Fg parallel divided by Fg, which is the hypotenuse. So that is the sine of theta. Therefore, if I want to find the Fg parallel, I can make it the subject of the formula by multiplying both sides by Fg. So that becomes Fg sine theta. I believe Mukove is seeing that. In the same way, how do you then use cos? So you use sine when you're looking at Fg parallel, because this is opposite the angle. Now, if you want to find Fg perpendicular, you would see that you need to use cos. Where does it come from? The cos of the angle theta is adjacent. What is the adjacent side to the angle here? It is Fg perpendicular divided by the hypotenuse, which is Fg. All right. Now, find Fg perpendicular. That will be given by Fg times the cos of the angle theta. And that is where the cos and the sine come from. It is all from your trig ratios, and therefore working out what the other sides are. One side is Fg perpendicular, the other side is Fg parallel. Right.
I'm trying to think if we've got time.
Yeah.
We don't have time. Okay, so says James.
All right.
Yes.
So apparently we don't have any more time for more questions, but I believe you have learned a lot from that.
Okay. Thank you, TK, for the lesson. Enkosi nakunike mindset ngokuthi nisijoine namhlanje kwinkqubo yethu. Sizawukunibona kule veki izayo. We love you very much. Bye, guys.